All right, anybody have any homework questions? Homework questions, anybody? All right, so we're starting with, hey everybody, shut up. Are you being a troublemaker? Me? Yeah. Are you gonna be a tough case? No, I'm going to get a chair eventually. I'm just waiting until I'm tired. Okay, so number 1 and 2 on the energy homework. So number 1, object moves from is this going? It moves from the point -3, 2 to 6, +1. Under the influence of a constant force, 50, 100 newtons. And these distances are in meters. What's the work done by the force? And does it add or remove energy from the object? Okay, so how are we going to calculate this? Well, anytime we have to calculate the work, we're hoping we're not going to have to do that integral, the line integral thing. And in this case, we don't have to. It's a constant force. And so that means that the work is just equal to the force dotted with the displacement. The displacement is the later position minus the earlier position. So 6, 1 minus -3, 2. So that's 9, -1. And so the work is, what was it, 5,100? 5,100 dotted with 9, -1. And that's 50 times 9 plus 100 times -1, which is 450 minus 100, so 350. And if distances are meters and force is newtons, what are the units? Newton meters, which is joules, yep. And then part B, is that adding or removing energy from the system? And how do you know? It's positive, so it's adding energy. And then number 2 is exactly the same. Okay, let's skip number 2. So now we're going back to what we were talking about on Friday. Back to And this topic deals with the work energy principle. And conservation of energy, mechanical energy. So far we've talked about the definition of work. Done with that. Now I'm going to, and we talked about two important force types that don't do any work. So that means when these two force types are acting in a problem and you're using an energy approach, you don't even have to do the calculations of work for those. That's great. So what two forces were those? Yep. Very good. Very good. Centripetal. And we did that. So now we have to talk about the work energy principle. Potential energy. And then finally, conservation of mechanical energy. And this topic is sort of, I don't know, it's the flow of it feels sort of odd to me, but I can't think of a better way to go through it. We need to build up all these concepts so you know when you can apply stuff. But really, all the problems that we're going to do, with very few exceptions, are just going to deal with this final step, which is sort of the most simplified form, but that's when this energy method is most useful because it makes problems so simple to do. So anyways, we have to start with the work energy principle and build up from there. And the example problems that we've done so far really suggest the work energy principle, so this isn't going to be a surprise. But I haven't put it in like an equation form yet. And so the work energy principle says the total work acting on an object done on an object is equal to the change in kinetic energy. So this is when I was sort of describing the intuitive way of thinking about, so remember the examples we did were the guy on the elevator. If the elevator didn't change speed, we thought of that as like a change in energy. And so if the elevator didn't change speed, the energy stayed the same, and so the total work was equal to 0. If the energy was speeding up as it moved, then the kinetic energy, the energy was increasing, and that meant that the total work had to be positive. If it was slowing down, the total work would have to be negative. It would have to be a net energy being removed. And so that's what this is saying. None of the things that we're dealing with have changing masses. And so if you have positive work, the speed is increasing. If you have negative work, the speed is decreasing. Could you stand up and give us a little twirl? I'm just kidding. Okay, positive work means the speed is increasing. What? Yeah, speed is always positive. What? Up above? Well, that's the order of topics we're going through. So these two, you know what those mean. These three, you don't really. Well, now I've given you the work energy principle. But this is just the flow of the things as we're going to discuss them. So negative work means the speed is decreasing. Okay, so let's do an example of a block sliding on an incline. So let's say this angle is 20 degrees. There's no friction. Well, we'll do one with friction and one without. So let's say the block slides down the ramp 1 vertical meter. So the distance it travels isn't 1 meter. That's the loss in altitude. Okay? So if we were using a Newtonian approach, using Newton's laws, we need a lot more information than this, but we're going to see that this is enough. So the block slides down the ramp 1 vertical. Yeah, or at least that's the amount of sliding that we're doing the calculation for. And we want to calculate the change in, well, let's say starts at rest. So what's the final speed? First, with no friction. And second, with a coefficient of kinetic friction of 0.1. All right, so first we're going to do it with no friction. And so we have to think about what forces are acting, because we're going to have to calculate the work done by each of these forces. So what forces are acting if there's no friction? Yes. And that's just mg, we don't know the mass. And one more force, normal, yep. Okay, so we know that the total work is going to be the work done by the weight force plus the work done by the normal force. And what do we know about those that makes us just giddy with joy? Yes. So the normal force is something, but it doesn't do any work. And so in this approach, I mean, just being totally... I can't guarantee that you did, but I definitely said it. Okay, so all we have to do is calculate the work done by the weight force. And the work done by the weight force is equal to the weight force, which is 0, negative, I'll call it 9.81 m, dotted with the displacement. What do we know about the displacement? Well, I want to show you. So we know that the vertical displacement is 1 meter, right? Let's say, obviously with that 30-degree angle, we could figure out what the horizontal displacement is. Oh, and this is down, so negative, right? Let's just call that h, okay, because I want to show you something about this.
So is the normal force always 0 or only 0 if
Always. If the thing is sliding or rolling, there is no work done by the normal force, always. And almost every problem we do is going to take advantage of that. That's probably the number one thing that sometimes makes the energy approach easier than a Newtonian approach.
So if the object's sliding or rolling, the normal force never does anything.
Right.
Okay.
That's right.
And that's because why?
Well, okay, so, all right, so notice that I didn't even bother to calculate the horizontal component of the displacement. I just called that h, because of what happens when we take this dot product. 4 times h, no matter what that is, that goes away. Plus negative 9.81 m times negative 1 gives us a total work of positive 9.81 m newtons. The newtons off. And that's not newtons, it's joules. Okay, so that is our total work. Okay? Got it? So the horizontal, so one thing this says is, well, let's finish the problem, and then we'll talk about that. That's not a mass, that's a displacement. So since it lost 1 meter of height, it had since its final height was 1 meter less than its starting height, because it went down 1 meter.
So the work of mass times gravity is just gravity.
Yeah. And so the work energy principle says 9.81 m is equal to the final kinetic energy minus the initial kinetic energy. It starts out at rest, so what's its initial kinetic energy? And so this is just equal to 1/2 m v final squared. You can cancel the m's, and you get v final is equal to the square root of 19.62, which is, what's that, 4.45 or something? No, I'm using the newest equation. Oh, yeah. That's kinetic energy. Okay, 4.43 meters per second. That's what the work energy principle says. That's what this is. T, yes, T is kinetic energy.
So also it's the change in kinetic.
Right.
I thought that meant time.
Yeah, you would think so because kinetic energy doesn't start with a T, but that's it. Okay, so I want you to notice a couple of super trippy things. Question? Down or up? Sure. Okay, so what if that ramp wasn't there at all? And if the ramp wasn't there at all, and we had done this calculation as the thing just free fell 1 meter, what would be the final speed in that case? Exactly the same. Isn't that sort of weird? So if there's no friction, really what it is if the only work is done by gravity, it doesn't matter whether this thing goes over a funny path to a height drop of 1 meter, or whether it falls straight down. The direction of the velocity will be different, but the speed is the same. Yes?
So if gravity had been, oh yeah, like it doesn't matter how fast it falls, does it?
Well, let's see. Yes, it will matter because when you do the change in kinetic energy, this is the final kinetic energy minus the initial. So if it starts out going 50 meters per second, that change in kinetic energy is 1/2 mv final squared minus 1/2 m 50 squared. The horizontal motion didn't matter. And so the work done by gravity only depends on the height change. Okay, so I wrote a lot of extra stuff here because I'm sort of introducing this new topic. Even with the extra stuff that I wrote, notice that problem is unbelievably easy, Yeah, shockingly,
I can't believe it's so easy.
Yeah, you would think, is it April 1st? No.
Wow.
This is real.
That's amazing. There's a lot of stars all over it.
Yeah. I know, my handprints are getting worse. I think some setting in my computer changed or something. I gotta find it again. Okay, but now let's do it with, when we do Newtonian approach, adding friction to a problem didn't add that much extra difficulty. So hopefully it'll be the same here. It doesn't make it terrible, but it takes it from being super, super simple to really not any easier than using a Newtonian approach. So now the coefficient of kinetic friction is 0.1. Well, one thing we have to do is figure out what the friction force is. And so let's look at a free body diagram again. The weight is 9.8. I'm just, you, they don't, yeah, they didn't hear me say that. So, okay, everybody listen to what I'm saying here, because this is physics class and we have to deal with physics. Okay, so what's the direction of the friction force? Yep. And that's equal to 0.1 times the coefficient of friction. Nope. Times the normal, you're right. Okay. And so from this, what can we figure out? Well, the normal force, we have to calculate what that friction force is. So what do we have? In this, let's use a rotated coordinate system. So this is going to be 9.81 times cosine and sine of 290. Can someone calculate that? $3.355, okay.
And then negative
218. Okay, and then plus negative 0.1 n. And then positive n. And then, right. And so now we have this times mass times the acceleration vector. We can calculate n is equal to 9.218. And then we can calculate that the force of friction magnitude, that's this, is equal to 0.1 times 9.218, so 0.9218 newtons. Just a magnitude. That's all from just the trigonometry. 9.81 m. Oh, and this should have an m. Sorry. This should have an m. This should have an m. And so the normal is this, and this has an m in it. Okay, we did that all to figure out that force. So the total work is equal to the work done by the weight plus the work done by the normal force plus the work done by the friction. And even with friction, no matter what, this is equal to 0. So we just have to deal with these two. The work done by the weight is exactly the same as it was before. That's just equal to 0, negative 9.81 m, dotted with something, negative 1. Same as before, and we just get 9.81 m positive. The what?
The force, when you calculate the force.
Mm-hmm.
Just the normal force?
Yes.
Why do you ignore like the acceleration?
Because there's no y component of acceleration.
Oh,
So we're just using the y equation.
For the normal force.
Right.
But then for the SS.
Oh, okay. So the friction force is just negative 0.1 n in the x direction, 0. So once we find n, we can calculate that force.
So you
And that's just a magnitude.
you ignore the 3.25 times.
Yep. Because all we're trying to find is the force of friction. This is a weight force.
Oh, that's just the force. Oh,
Yeah.
no.
And now we can calculate the work done by the friction force. And that's equal to, okay, well, let's use this. So the work done is going to be using that second definition of dot product. It's going to be the magnitude of the force of friction times the magnitude of the displacement times the cosine of the sine between them, of the angle between them. Okay. Well, now we have to figure out that distance. We know that this is 1. We know that this is 20. So I'll call this capital H, hypotenuse. So 1 over capital H is equal to the sine of 20. So H is equal to 1 over sine of 20. What's that? Are you in radians? Oh, yeah, right. 2.92. Yeah, I thought it was going to be smaller. Yeah, I really apologize. Yeah, yeah, right. Only 2 significant figures. Okay, so.
Okay, wait. How do we know? I know that like U and V times data.
Mhm.
Yeah. How do we know that U and V are at friction force and V?
Because the work is the dot product of the force vector and the displacement vector.
So U is the force vector.
Right. Yep. Yep.
Always.
Well, work is always the dot product of a force vector and a displacement vector. So the force is always one of those, and the displacement is always another one.
Force is always a dot product of a force.
Yep. Question, Jeannie? No? Okay. So this is the work done by the force of friction is, what's the magnitude of FF? That's what we just calculated. 0.9. What is it? 0.9218 m. No. And then the magnitude of the displacement is the distance traveled. That's 2.92. And then that's multiplied by the sine of the angle between those. What's that? Yes, cosine. Sorry, no. Okay, so what is the angle between the displacement vector and the force of friction vector? Ron? More than 90. We know what it is because the displacement vector, but the force of friction vector is up the ramp. The displacement vector is down the ramp. It's 180. Is -1. So, yeah, so we get negative, what did you say? 2.69 m. And so now we can finally use the work energy principle. And the work energy principle says add up the work of all those forces. So the work done by gravity is 9.81 m. Okay. The work done by friction is negative 2.69 m. And those are equal to 1/2 mv final squared.
Okay, so for the beginning, we used the displacement vector as the total height it went down, right? But for this one, because it's on the ramp, we use h for the displacement vector.
Well, we used, so displacement is a vector that is, its magnitude is the distance, okay? And so if we're using the first definition of dot product, where we use the components of the vectors, then it turns out that all that mattered was the vertical distance, because we were taking the dot product with the weight force, which only has a vertical component. It was easier to just do it using the second definition of dot product, because the distance traveled is parallel to the friction force. Right.
And we still have to multiply
By cosine. I said sine, but this is the second definition of dot product
cosine.
of the angle between those two vectors.
Or it's the angle between, so it's not the angle that
No, it's the angle between the force vector and the displacement vector. Okay, so what's 2 times 9.81 minus 2.69? That's, so VF squared is 14.24. And so V final is what? 3.77 meters per second. Okay, so look at the amount of work we did when there was no friction. Basically nothing. I mean, yeah, basically nothing. It's way easier to do it with no friction using energy than to use Newton's laws. Yeah. It actually reduces work though.
Oh, it adds more work for us.
Right. Okay. But look how much work it took. Look how much writing it required to calculate when we did include the friction. So notice the energy approach. Yeah. Energy approach can be way faster in certain problems with no friction. Including friction can make it, a lot more complicated, a lot harder. Okay, so that's the work energy principle. That's the basis of the solution approach that we're going to use. In problems with no friction, this is still part of this notice. So how do you know generally when you want to use a Newtonian approach and when you want to use an energy approach? In problems with no friction, use the energy approach if the problem statement, this is going to be on your next quiz, this question, something about this. If the problem statement relates a position change speed change. And it turns out that that's true even if you're talking about angular speed and angular velocity. But so if you have a calculation where you're asked to determine the acceleration or something, or just figure out a position vector given forces, you probably still want to use a Newtonian approach. The thing that should trigger you to consider an energy approach is if it says something about like the object moves from here to here, what's the change in speed? Or what's the speed at the bottom of this hill? Or when the speed gets up to 30 meters per second, how far has it traveled? Something like that. Those are hints that you should use an energy approach. Okay. Yes, still writing. So now the next thing that we have to talk about, really this is enough. We could stop here and it wouldn't, this is a really useful way, but we're going to simplify it a little bit more. For the problems we're going to do, we can do these calculations a little bit more concisely if we deal with conservative forces. Although it's true that it is related to conservative, but I wasn't going to say that. I was going to say conservative forces and potential energy. And so a conservative force is one where knowing the object's position is enough to know the force. We're going to deal in this class with two conservative forces. So there's just two conservative forces. Those are the weight, force applied by gravity, and forces applied by springs. Okay, so let's think about how this. The force is determined by the object's position. So now let's think of a couple examples of non-conservative forces. And if you're trying to think of a so cable tension, normal force, friction, and a million other things are non-conservative. Conservative forces can be thought of as force fields. And conservative forces, and only conservative forces, have what's called potential energy. And I'm going to define, I'm going to call potential energy, every class calls it something different. I guess I'll call it uppercase U. Okay, so before we take a break, a force field, what does a force field mean? It just means that basically, like, if the position is enough information to specify the force that's applied to an object, you can imagine those forces just waiting in space for the object to get there. And wherever the object is, that's the force it gets. You know what I mean? So gravity is, the gravitational force applied to this is a force field where at every location you just have force vectors going down at 9.81 times m. Okay, and it gets there, and now it gets this force. So it's a field like a beautiful poppy field. Like, I love this field. Everywhere I go, there's a poppy to sniff or whatever, you know, to make friends. But gravitational is the same way. Like, look at all those gravitational forces. If I go here, there's one, and if I go here, there's one. You know, so that's what a force field is. And it's not as cool as like in Super Friends. Yep. It's not dependent, but the question is just, is position enough information? Right. But for a spring, it is dependent on the position. And you can think about it the same way. There's all these forces. What?
But not in summer.
Right. Only in spring. No, that was a joke. Don't try to make sense out of that later. So a spring force, you can think of spring forces waiting in space for the object to get there. And if you go here, that spring's there waiting for you. If you go here, that force is waiting for you. Yeah.
Someone opens the door, the spring is there.
No, not the spring, just a force. You can't see it. You have to imagine it. Yes. Okay, so let's take a break and come back at 9. And I think, so we'll talk about how to calculate potential energy. And that's going to be great. Remember our deal. You listen to me now, you talk in your other classes later, as loud as you want. Okay, so potential energy. So here are the potential energy functions for our conservative forces. So how many potential energy functions do I have to give you? 2. Weight and spring forces. Okay, so the first one is for weight. So choose height to call your zero height. So you get to choose that. You know, if you want the ground to be what you call zero height, the center of the earth, the sun, whatever, you get to choose a zero height. Then the potential energy due to the weight is equal to the mass of the object times 9.81 meters per second squared times the height relative to your zero height. It doesn't have to be that. That's a kind of an intuitive way to think about it, yeah. But yes, so that's definitely the idea of potential energy is it's energy that this thing has that's waiting to be used. So if I'm holding this stapler up here, there's mg times 1 meter of energy that's waiting to be used to speed this up if I let go of it. That's the idea. And then for a spring force, let K be the spring constant. And X is the distance from the spring's resting length. Then the potential energy is equal to 1/2 K X squared.
Wait, so the first one we just choose a height called zero height?
Yep.
That's it.
And you have to use it through the whole problem. So if you think like, well, I'm just going to choose it where the object is, and then it never has potential energy. Well, it would have zero potential energy at that one instant. But as the problem goes on and the object moves around, it would have potential energy. But there's an arbitrary constant that you're always just sort of subtracting. Yes, but that's right. But gravitational potential energy can be negative. The reason for that is all we care about is the change in potential energy, and we'll see why in a second. Yeah. So notice our h equals 0 location is arbitrary. Because all that matters is the change in potential energy, not individual potential energies. Okay. So why is potential energy? Well, let me do an example. So let's say you have a spring hanging vertically attached to an object that has a mass of 10 kilograms. And let's say the spring constant is 500 newtons per meter. And let's say that our H equals 0 is the object's location when the spring is at its resting length. So what's the total potential energy at equilibrium? I think this is going to come out to be 0, actually, now that I think about it. What?
What is equilibrium?
That's when it's not moving. So it's hanging there. So the spring's resting length is, say, 10 centimeters. And then you hang this mass from it, and the weight of the mass stretches it a little bit. Okay. So we'll see. Okay, so we need the potential energy due to, well, first we have to figure out how long the spring is. So a free body diagram. We have an upward force of negative 500 times, let's say our x direction is positive up. Okay. So then, since our we'll set our x equals 0 at spring's resting length. So let's just think it through. So negative 500 times x is the force, and we have the weight down of 98.1. So we're going to think that. Okay. So if x is positive, okay, if x is 0, the spring's at its resting length. So that force is 0. Okay. You with me so far? Yes. If x is positive, then this is shorter. Okay. And that means that the spring is pushing it down. And so the direction would be opposite of this. And so that's what that negative does. If you pull this down, x is negative. Negative times negative is positive, and so the force is up. So that just gives us the right direction. And then Newton's second law in that x direction says negative 500x minus 98.1 is equal to 0 because we're in equilibrium. And so x is negative 98.1 divided by 500, 0.19 something. Okay, so now the potential energy. The potential energy, gravitational, is the mass, 10, times 9.81, times the height. What's the height h? Our zero height is our resting length of the spring. And so this is 0.196 meters below our zero height. So, oh, yep, it's just that, 0.196. And can someone calculate that?
Negative 19.24.
19.24 joules. That's pretty close.
1962.
And then the potential energy due to the spring is 1/2 times 500 times the distance the spring is stretched or compressed from its resting length. So we can just use that same number, negative 0.196 squared. The square is going to get rid of the negative anyways. And what do you get for that? My vote is for 19.23, but I'm not totally sure about that. $9.6? Oh, well, there you go. The first time I've ever been wrong. Yeah, I made it this long. I feel pretty good about that. But. And so the total potential energy is negative 19.23 plus 9.6. And what do you get for that? Negative 9.5. So that's how you calculate potential energy. Why do we care about potential energy? You may be asking yourself. I'm about to blow your minds. We care about potential energy because the work done by a force is equal to the negative change in potential energy. And so we can use the change in potential energy in the work energy principle instead of calculating the work with a dot product. Can we do it for every kind of force?
Nope.
Only conservative forces.
So how do we know that B equals that X value?
That what?
Like for the 1/2 what does the B stand for?
Speed.
So and the X is that speed?
No. In this problem, we were just talking about this thing hanging there. So there was no acceleration or anything. We just calculated this X so that those forces balance, so there wouldn't be any acceleration.
And why is down there, why did you use that for B, that number?
Oh, I didn't. This form looks a lot like the form of the kinetic energy. But this is the potential energy for a spring. So kinetic energy is 1/2 mv squared.
Oh, and this is kx.
Yeah,
Oh.
spring potential energy is 1/2 kx squared. So the form is the same, but they're not the same thing. No, don't write that down. Okay, so for conservative forces, otherwise there's no such thing as potential energy. You can use potential energy the work energy principle. And if the only work is done by conservative forces, and really that's most of the problems that we're going to do, so if the only work is done by conservative forces, the work energy principle reduces to conservation of mechanical energy. Where the total mechanical energy is equal to the kinetic energy plus the potential energy. So let me show how this works. The work energy principle, where only conservative forces do work. Okay, so the work energy principle says the total work is equal to the change in kinetic energy. If all you have is conservative forces, then the work is equal to the negative change in potential energy, U. And that's equal to the change in kinetic energy. And then you can write that as the change in U plus the change in T is equal to 0. Or what that says is U plus T at instant 1 is equal to U plus T at instant 2. Okay, so that's conservation of mechanical energy. So let me do an example. Anybody have any questions yet? Okay, lay them on me. You don't even know where to start. I know that feeling. Yes. 42. Yes. Why does it have to be a man? So here's an example. So this example is going to show the sort of beautiful simplicity of all this. So let's say this is Morgan Gasser. Is she still in your school? This is her at the top of a hill. Yeah. Isn't that what she does?
I don't know who she is.
Oh, she skis. She's a really good skier. She's just going to go straight down because if she does any of this stuff, she's building up friction and that messes up the simplicity. So she's just going straight down, friction free. And let's say, let's say that this hill is, let's say it's just 10 meters tall. She starts at rest. How fast is she going at the bottom? So first of all, why would we think of using an energy method for this? What's the...
No friction.
No friction.
The change in speed.
That's right. Very good. So you look at that and you think, I'll bet this is a... Don't leave her hanging. So you look at this and you think, this is probably a good problem to use an energy method for. If we were not going to use an energy method, we could do this problem if we knew stuff about the shape of the hill, you know, and we could use Newton's second law to calculate acceleration at each separate spot on there, and then we would integrate it with respect to time to get the velocity. It would be a huge pain. But look how simple it's going to be here. Okay, so Freebody diagram. First, we have to make sure that there's only conservative forces. So, okay, so there's the skier. Where are the forces acting?
Gravity.
Yep.
Normal.
Right. No friction. We're ignoring it.
She is super fast.
Yeah. Or if you're at Buckhill, right into 35W.
Yeah.
Okay, so conservative forces, we have the weight. Non-conservative forces, we have the normal. So are we screwed?
Well, normal doesn't work, right?
Exactly.
It doesn't matter?
So it doesn't matter.
Yes!
High-fiving injury. Okay, so that means we can use conservation of mechanical energy. Our quiz on Friday is going to be nothing but questions about when you can use what, when there's a potential energy function, what forces are. Okay, so we're going to use conservation of mechanical energy, and I'm just going to set it up like this. There's a little table. One side is instant 1, one side is instant 2. I'm going to set this as my height equals 0 at the bottom of the hill, because why not?
That makes good sense.
You could put it anywhere you want. Okay, so at instant 1, at the top of the hill, what's not moving, so what's the kinetic energy? That's right. And what's the potential energy? 9.81 times m times the height. What's the height? 10. Oh, yeah, really?
Yeah. Like you lose potential energy and get...
Yeah. In 6th grade?
No, we did stuff.
Okay. So there's the potential energy at the top of the hill. Now, at the bottom of the hill, what's the kinetic energy? 1/2 m, and then we don't know the speed, right? That's what we're trying to find. So this is just v squared. And then what's the potential energy? Right, 9.81 times m times 0. So this is 0. And
Instant 1 equals T instant 2.
that's right. So conservation of mechanical energy, cum, is equal to 0 plus 98.1 m is equal to 1/2 mv squared plus 0. Cancel the m's. And you get that v squared is equal to 196.2. So V is equal to 14.01 meters per second. So just like that, in just a few lines, we calculated this thing that would have been a major, major hassle using. Okay, gotcha.